All right. All right. So how did the universe start? When did the first atoms form? And how old are the atoms in your body? Well, um, the short answer to that is your atoms are as old as the universe itself. Everything's been recycled. So we are made out of recycled stardust. When did the first stars form? And what came first? I put this on the discussion board and you can tackle this topic, which is debatable. Was it a star or galaxy that formed first? What is the shape of the universe? What is the center of the universe? And what is the ultimate fate of the universe? Well, the ultimate fate of the universe is not known yet. We're still trying to do the numbers, and the numbers are mind-boggling. So just be aware, have some patience for cosmology. You just want to take a few items home. You don't have to understand everything there is to know about cosmology today or ever in the next few years. It takes some time, but the idea is to put some of these pieces together bit by bit. So it forms a picture and gives you an idea of what some of the subject matter in cosmology is, and gives you some basis on a picture of what the universe is and what it looks like and what it's evolving into. Okay, so there's a lot of images out there, and the problem with cosmology is the fact that we create a lot of illustrations and we try to describe things in words, but ultimately when you're trying to explain the state of the universe, what it looks like, its shape, for instance, and what its fate is, it really is all dictated by the numbers, okay, and the theories. There's a lot of mathematics and physics involved that really give you the ultimate picture. For instance, if you were trying to describe the law of gravity, you could describe it in words, but that really doesn't give you a fundamental understanding of the law of gravity. It really comes down to how the formula works, or in an updated version with Einstein's general theory of relativity, which is a complete theory of gravity. It gives you a way of describing using mathematics how space and time are curved through gravity. So you actually have the numbers that tell you the equations that give you that picture. Okay, there's no other replacement for that ultimately. So that's why there's a lot of requirements in learning a lot of the formal mathematics and physics and in doing astronomy and things like cosmology, the subfield of astronomy, a subfield of astronomy. Okay, so we get a lot of these pictures. And the idea is that we all start from this little point called a singularity. So what you have to try to envision is the beginning of the universe starts at this single fine point. If you crunch everything down to that single fine point, that's how we started. Okay, so just some coming back to what we looked at the very beginning of the class. So we're going around in a circle here, right? We're going to address some of these questions that came up at the very beginning of this course. So when we talk about universe again, we talk about everything, all the matter and energy and all the space-time that it's contained in. Okay, so that's everything. So we know that everything is big and there's a lot of everything. So we've learned a lot of these inhabitants of the universe, right? We have stars, galaxies, planets, moons, asteroids, comets, meteors, gas and dust. And then we also have some mysterious stuff like dark matter. And I should add dark energy into the picture too, because matter and energy are same sort of thing. So what we have, I should say, well, dark matter and dark energy are different, but we know that energy, mass is nothing but frozen energy. So that's a topic in itself. So important thing to distinguish between there. So anyways, we have a lot of inhabitants, but we also have a lot of empty space. And the temperature out in space is really cold nowadays. So we're talking about like 3 degrees Kelvin. And Kelvin is minus a lot of degrees Fahrenheit. So you could do that conversion. So very cold out there. So it's very spacious, very cold. And what we know currently is that, the universe is just growing, expanding, and cooling as it's doing this. Okay. The age that we have pinpointed, and something that you might come across it as a different number in different web references, different videos. So just be aware of the closest fine-tuned value is about 13.8 billion years. There's a plus or minus arrow bar on that. So that's our best estimate on how old our universe is. So we could look back to about 13 billion years. We could see galaxies back that far in time, but we haven't been able to get beyond that limit yet, all the way up to 13.7 billion years. We haven't been able to look back that far yet. So that's how old it is. So we have a lot more to go. The size, this number I put down is confounding, really a hard number to get, because the problem is a lot of people say, well, it's 13.8 billion light years. That's not true, because as the universe started in that time, it's been expanding, accelerating, so it's much larger than that number. Some people have actually put that number together and you could reference it. There's a lot of calculation behind the size, but the size is huge, much bigger than 13.8 billion light years. So don't make that mistake. The center is everywhere and nowhere. There's really no center. So we'll get into that topic a little bit. And the shape is flat. Current evidence is that it's showing this flatness. Now, not flat, two-dimensional paper flat. Okay, that's a different kind of flat, which we'll talk about. And the future end of the universe, well, that's still under investigation and debate. Okay, but we do know, here's some stuff we do know. We have evidence for the birth of the universe, and which is called the Big Bang. And that's our model on how the universe was born and has been evolving since then. So we have to think about everything, all the matter in all space-time crunched up to a little point dot called a singularity. Okay, so we squeeze everything back together. That's a lot of stuff. So that's a point of infinite density and energy. So there's so much stuff packed in there. Now, all we know with the Big Bang is going from that singularity, that point of all mass, space and time, to what we know today. We don't know anything before. In fact, you cannot even ask the question, what happened before the Big Bang? What happened before the Big Bang? Because the Big Bang explains how space and time itself started. Okay, so you have to remember the time aspect. Before the Big Bang is not a valid question, because time didn't exist before the Big Bang as we know it. Now, there's a lot of proposals and there's other theories out there about maybe some other occurrence event that perpetuated the Big Bang. Maybe it's part of a collision with another universe. And there's some ideas in this multiverse theory out there that propose similar sort of scenarios for the cause of the Big Bang. But you cannot ask what happened before the Big Bang, because time just did not exist as we know it before that. Okay, so just a small little outline on the Big Bang, and this can get pretty heavy duty in terms of science, so I try to condense it down as best as I could. Some important time epochs, and it's broken down into these epochs as far as the birth of the universe at time 0 to the universe we currently know of today. So at time 0, we have the Planck epoch, and we have something called the Planck time, which is the smallest increment of time possible. And so in the beginning, about 13.8 billion years ago, all matter and energy were compressed to a single point, a singularity. Okay, so what happened then is that this singularity began to expand and cool. And between 10 to the minus 43 and 10 to the minus 12 seconds, we have a few significant time periods: the grand unification epoch, inflationary epoch, electroweak epoch. Oops. And the quark epoch is coming up after this. But this is where the universe begins to cool and expand enough so that gravity separates from the 4 fundamental forces. So everything at the beginning is just like this hot, dense soup. It was so hot and so dense that the four fundamental forces were not distinct from one another yet, okay? And a lot of the scientists are trying to find something called the super force. At this time, we believe that all these four forces were combined into one super force, and they call these grand unified theories trying to figure out what that super force is, or guts. Grand unified theories, guts is the abbreviation for that. So everything was so hot, we didn't have gravity different from the strong nuclear force, and have that different from the weak nuclear force, and have that different from the electromagnetic forces. So just as a little recap, the four fundamental forces are what operate and change the motion of all the objects we see. They're their hand responsible for all the dynamics in our universe that we know of. Okay, so what happens is, in this little time period, we finally get gravity to separate from the other three fundamental forces. And then we also, then shortly after, we have this period of expanded, accelerated growth called cosmic inflation. And I have a future slide on that. And then we finally get the strong nuclear force separating from the others. And eventually all four of these forces become their distinct forces. Okay, so it still continues, expands. The universe cools, expands, because as you expand, you are cooling in the process. And it finally forms these quarks. So this next period of time, we have the quark epoch, hadron epoch, and the lepton epoch. So here we're getting into fundamental particles, this is again of great interest to a lot of particle physicists and a lot of those experimenters at CERN. Quarks are the most fundamental particles, and they form protons. They have combinations of quarks that form some of the other subatomic particles. So the smallest particle you could get is quarks, and it's combinations of quarks that make everything else. Okay, so anyways, it begins to cool, and then we start forming some of these quarks. We start forming these electrons and neutrinos. And leptons form, such as electrons, providing mass and energy photons. We start getting mass and energy at this point, and photons created. So without going into heavy particle physics here, I'm just going to have this little summary. And then when we get to 3 to 20 minutes, and then 20 minutes to 240,000 years, we get the process of nucleosynthesis. And that's the process of fusing elements together. Okay, so we have atomic nuclei able to fuse, and then we get the energy dominated by photons. So we got a lot of photons created and being emitted, absorb, re-emitted, absorb, re-emitted. So we have a lot of energy, and that high energy at this time is what we're having evidence for as far as the cosmic microwave background radiation, the afterglow of the Big Bang. Is we could see these photons in stretched out wavelengths, which we'll talk about in the next slide or two. Okay, and then what we have is we have a little period where the temperature falls to 3,000 degrees. So this is significant. We're going from like billions of degrees to 3,000 degrees. And what happens is the photons start to travel freely, but no stars are formed yet. We're talking, this era is dominated by dark matter. And again, the theory here is still under investigation, because dark matter is really responsible for providing that scaffolding, that framework for galaxies. So, you know, we don't know if the galaxies are being formed first and then the stars, or vice versa. And the next really significant period is we have the energy, the matter, regular matter, visible matter, the matter that interacts on a daily, that we're familiar with on a daily basis, is starting to become like energized. And what happens here is we start getting small little irregularities in the gases. So again, here we're mostly looking at hydrogen and helium. And these slight irregularities in these gases or these gas clouds are what's creating the first stars to form, right? So we know that you have these clumps of gas, and then what happens is as gravity acts on it, you get these first stars forming. It starts condensing and collapsing to create the conditions for hydrogen fusion to occur. So the very first stars, which we're still looking for, are these supermassive, short-lived stars. Okay, they gave way when they gave way to the next two population stars that we are familiar with today. They were recycled and then brought about our current stars. So at this point, after 500 million years and on, is when we really have our structure fine-tuned. At this point, we're having the first stars. They are huge, so of course they would have short lifetimes, right? This is one of the challenges in trying to find them or evidence for them. So they have short lifetimes, so they go supernova, and then the remnants of those supernova provide the elements that bring about the next generation of stars. Okay, so then we also have galaxies that are in formation, the first galaxies, and then they start colliding with other galaxies to form the galaxies that we see today. So from 500 million years to now, 13.8 billion years, we see this structure. Things have cooled enough and progressed, and a lot of collisions have occurred since then. And we're also talking about a huge increase in size, okay, since then. Now, the evidence for the Big Bang, you know, if anybody says, well, the Big Bang is just, do you believe in the Big Bang? Which is erroneous to even ask that, because it has nothing to do with belief. It's just, you know, when you're in science, it's based on evidence and what the evidence provide. It's a matter of, okay, do I see enough supportive evidence for the Big Bang? That's a better way to question it. And there is key evidence. The biggest key part of it is going back to, I'm trying to find a date here, hang on. It was Roger Penzias and Wilson. I think they were working for Bell Labs, and I'm looking for a date. Penzias and Wilson, yes. They discovered this cosmic microwave background radiation by accident. Now, the date I'm thinking is the 60s, but don't quote me on that. I'll have to add that in here. They were working for Bell Labs, and they had these radio dishes pointing at the sky, and they kept getting this static, right, in their signals. So they were using radio dishes to collect radio waves, and they kept picking up static. So no matter where they point in the sky, they kept getting this static, this noise in their system. So what happened is they thought, well, maybe there's birds nesting in our dishes. So they clean out the dish, make sure there's no pigeon poop or anything in there, etc. They clean it out, and again, they find the same noise. So this occurred, and it was like, it's like one of those moments where you go, something else is happening that's interesting. So they found that no matter where you point these dishes, you still, in whatever section of the sky you point these radio dishes at, you will get the same radio signals, the same noise. And that noise, that background noise, is what we call the cosmic microwave background radiation. It's in the microwave part of the spectrum. So you could go back to our light slides. There's a certain wavelength associated with the cosmic microwave background radiation and frequency. And this was everywhere. And this noise was consistent throughout the universe. And what happens is, this is the afterglow of the Big Bang, so to speak. So when the big explosion occurred, the Big Bang occurred, things were really hot. We're talking, again, really high temperatures. And the first photons were high energy gamma rays. So as the universe began to cool and expand, those high energy photons, those wavelengths have been stretched out. So think of a wave, right? Really high frequency wave that's just been pulled and stretched across space. It's been pulled across space. So the frequency has decreased, the wavelength has increased over time, over 13.8 billion years approximately. And this was a significant finding. And of course, we're constantly mapping this cosmic microwave background radiation. I put WMAP, which is one of our data taken satellites. Ran from 2001 to 2010, and it mapped this background radiation. But we have other satellites that have mapped this cosmic microwave background radiation. So we have this radiation, we have all this radiation evenly distributed all throughout space. Now, one of the fun things is you have evidence for it if you have one of those old televisions that still pick up static, right? You get the static on your television. That is the cosmic microwave background radiation. That's static. And so it's everywhere, and you could pick it up. So you could, if you decide to create your own radio dish, you could pick it up as well and get that signal. Okay, so big supporting evidence by that. So anyways, the next is the redshift of galaxies. We talked about Hubble's law, and we'll revisit that with some added notes to Hubble's law and the redshift of galaxies. So what Hubble found in 1929 is that the galaxies, as he was mapping them, were moving further away from each other. And the further a galaxy was, the faster it was moving away. And this created a Doppler shift. So remember the spectra, the Doppler shift is if an object is moving towards, or if two objects are moving towards each other, it could be one object or two. If they're moving towards each other, the wavelengths are shortened so that they're called blue shifted. If an object or two objects are moving away from each other, then the spectrum, the wavelengths are what we say red shifted. They're stretched out, and the wavelengths are longer than expected, longer than emitted by the source. Okay, so the redshift means that these galaxies were receding away from us and at a pace so that further out they were moving faster and faster away. Some other lines of evidence are the mixture of elements that we have. So one of the big things is, the proportions are explained by those epochs at the very beginning of the universe and by those temperatures. So the way the elements are distributed, the distribution of those elements are based on the recycling of stars, and our models clearly show how this occurs, how it is mixed as we see it today. The other is looking back in time, look back time. So the fact that we could look back and we could see we could see the light that's been emitted like 13 billion years ago, 10 billion years ago, gives us evidence that this has happened in history, that we could trace it down to a fine point. Okay, so some good lines of evidence. Definitely cosmic microwave background radiation. That's your number one line and the most used, the most familiar line of evidence. Okay, so what we found with the universe is we had the explosion happening, and everything's been expanding and cooling ever since. So as Hubble did in 1929, he plotted the galaxies and their distances and found the further out you go, the faster they're moving. And this is proportional to this Hubble constant, which we showed was about 70 megaparsecs. Okay, so again, this is a proportional, and this led to the idea that everything must be expanding. The universe is expanding. Okay, so the neat thing about the cosmic microwave background radiation is it finally said, oh, again, this points to evidence for the Big Bang, that we must have started out as a singularity. Okay, so important idea. So here's the redshift, galaxy redshift. So the idea is, if you have the emission of light, let's say here's a galaxy and you have these parts of the spectrum here. So these right here are absorption lines. Okay, so remember you have the rainbow with nothing on it, no lines in it whatsoever, is the continuous spectrum. When you have a rainbow with lines, black lines in it, means those are traces of elements that are being absorbed by a gas. Okay, Now, if those lines, if all you have are colored lines, those are emission spectrum. So here we have an absorption spectrum. So if it was stationary, if we were just looking at a galaxy, it was right in front of us and wasn't moving, we would see these key absorption lines in its spectrum, okay, based on what it's made out of. And then if that galaxy started moving away from us, we would see these lines shift. This is what we mean by a redshift. And galaxies further away than this galaxy would have lines further redshifted. The whole spectrum would shift to the right. Really important idea. So this is what we found. We had the spectral shifts showing all this. Okay. Now, the redshift of galaxies was key evidence that the universe was expanding. And it's not just galaxies, it's also groups of galaxies that are moving away from each other, because we have groups of galaxies that are connected in ways through gravity. So a good idea is to think about, you know, here we are in our initial state of the universe. So here's our galaxy, here's another galaxy, here's another galaxy. Or here, I'd rather say, is our group of galaxy, our local group. Here's another group, and here's another group. And what happens is, over time, is space is expanding, just like graph paper. So you would have this all expanded outward. And here's our local group of galaxies. Here's this other group of galaxies further away. Here's this other group of galaxies. So there are little islands of galaxies that are spreading further and further apart. So this is what we mean by the expansion. Now, again, we kind of fall short because we're doing this two-dimensional representation of something that's occurring in 3D. So a little hard to do, but that's the basic idea, is you're magnifying your graph paper bigger and bigger and bigger, and that's what's happening to our universe on a daily basis. Every second that passes, the universe is expanded and expanded and expanded. And that's why doing the distance calculations, like how big the universe is really mind-boggling. Okay, we do have the Cosmo redshift factor. We have a Z value that's often used. You'll see this come up in the literature. And this is your observed wavelength minus your wavelength given off at rest. So here's your rest wavelength. This is what it looked like if it were stationary. Then you would put in the observed wavelengths you see for here, the rest wavelength, then you get the Z factor. Okay. And there's other ways to compute this value, but it's used a lot as far as cosmological redshift goes. And one other thing I'm going to point out too, a good book for reference, you know, since we're grappling with this, you know, these two, we have to try to do these analogies, 2D analogies, 3D analogies for like a 4-dimensional universe, which is what we use to model the universe based on Einstein's theory of relativity. There's 3 spatial dimensions and 1 time dimension. Now, the pitfalls of that is like you always fall short of trying to describe the universe in that way. There's a book that was published in the 1800s called Flatland. And it was meant as a political satire, but it's been used as a reference by a lot of mathematics and physics students in trying to understand how hard it would be for a 2-dimensional creature to picture a 3-dimensional world. And that's sort of like us trying to piece together the universe. We're looking at 3D and trying to picture it higher dimensions. So it's a really good recommended read to try to grapple with that challenge of trying to picture a higher dimensional universe. Okay, so after the Big Bang, there's certain observations we made that really came to help us put together our theories. Let's sip of coffee real quick. We have an isotropic universe, and it means it looks the same in all directions with only local variations. So you could go on Earth, it looks the same in all directions. You could go to the moon, it looks the same in all directions. You could go to Pluto, it looks the same in all directions. Relatively speaking, you could go, I mean, for our solar system, it's probably, there's more variation. So to really get this isotropic view, you'd probably have to go, okay, here we are on Earth, but let's take a look at another part of our Milky Way. Let's go to another spiral arm and look around our galaxy and see what we see. And we'll see that it's relatively the same. And then homogeneity, on average, matter and energy are distributed evenly across the universe, right? So it's like if you have a cup of coffee and your cream is well mixed in there, everything is evenly distributed. There might be slight variations here and there, but on average, you have the same populations in all directions, same population of stars and galaxies. So we could be here on Earth looking at galaxies. We could go somewhere else and go look at galaxies. We'd have pretty much the same even distribution. And the cosmological principle refers to the universe is isotropic and homogeneous. Then it'll look the same to any observer in any part of it. So that just kind of repeats this idea of this incorporates the two above principles, two above ideas. Okay, there we go. So here comes the question of, I'm going to address the observable universe and the center of the universe. Now, the observable universe is what only we can see. So again, it's mind-boggling when you think about the universe expanding and cooling and going to the size it is today. So some of the questions that come up is, where's the center of the universe? What can we actually see in our universe? The universe is much bigger than the parts we could actually see from horizon to horizon. And we have experience with this on a daily basis, right? You go out to the coast, look out at the Pacific Ocean, you can't see beyond that water line, right? You can't see what's on the other side of the Pacific Ocean. If you do, I want to know what your secret is. But anyways, we are limited by what we can observe via the speed of light and how long it takes for that light to reach us in a position. So we don't have the ability to see beyond this observable universe. And the observable universe is what we see up to a horizon from our position on Earth. And that is only part of the overall universe. Now, the observable universe to another observer, let's say here we are in the center, because theoretically we are all the center of the universe. There's no real center to the universe. But if we were observing here, that would be our center, and this is what we'd observe, horizon to horizon. If we were on this edge here, we would make a new bubble, a spherical bubble around us, and that would be the light that we could observe. So somebody else's observable universe right here would be different than our observable universe. And it'd be nice to compare notes with somebody in that other section of the universe, but we haven't got there yet. Okay, so everywhere, nowhere is the center. There's no real center. The idea is that everything's expanded and it's homogeneous and isotropic in nature. So you go anywhere and you have the center. Everything is surrounded. There's no center. Mind-boggling. Okay, another important thing to take away is there's been some numbers that have confounded people working with cosmology and trying to understand the current state of the universe. And what we have, like, a certain way that the universe is flat. We have something called the flatness problem, and we have something called the horizon problem, which is I didn't put in here. But what we see today is not necessarily what is predicted by just expanding through the Big Bang. There had to be a time where the universe expanded at an accelerated rate, which we call inflation. Okay, and Alan Guth proposes in the 1980, and I have his book here. I'll have to start pulling all these books on my back shelf. There's a lot of good reads, but here's his Inflationary Universe book, Alan Guth, and that's part of his theory, and addressed a lot of these problems that we saw. And we had this accelerated expansion really early, like 10 to the minus 35th of a second. So that is like, you can't blink in that amount of time, very short increment of time. And then it settled down to a more sedate rate of expansion that we're currently seeing. So his reasoning too is that we have, like, the universe is huge, that we're only seeing a small observable part of this small region, which is why the universe appears flat to us, which is our current theory on the actual shape of the universe. Okay. So anyways, inflation is this rapid acceleration early on. And then we also have this added challenge now of this accelerating universe. So we looked at inflation. We saw that the universe started via the Big Bang. It's been expanding and cooling ever since. And then we had this period of inflation. And now we have the universe accelerating. Okay, so now it's what that means is it's speeding up and how fast it's expanding. So the speed is changing. So anyways, what's happening here is there was discovered supernova distances were shown to be further away than expected just using our basic expansion model. So this means that there's something making the universe accelerate at a rapid pace. So this is where we came up with dark energy. And this is this energy that exerts this repulsive pressure that counters gravity and accelerates its expansion. So this is what we mean by this accelerated universe. So dark energy is a type of energy that has got this repulsive pressure. We still have to find evidence for it, but it's inferred from all our observations. Now, a representation today of the mass energy of the universe is that we have regular atoms. This is our visible interactive matter that we see on a daily basis. Now, when we think about atoms, think this is 98% of these atoms are the hydrogen and helium atoms distributed throughout the universe that we see. Okay, most of the universe is hydrogen and helium, 98%. And then we got that 2% or less, which is the other stuff. Okay, then we have 72% that comprises of the dark energy. Now, then we have dark matter. We talked about it being majority of the mass of a galaxy, but now we're talking about the overall universe. Dark matter is, here it's estimated at 23%. So remember, dark matter is different than ordinary matter. It doesn't interact in the same way. It's not visible, but it has mass. So dark matter is different than dark energy. Dark matter is responsible for the construction of galaxies. It's why we have galaxies rotating at quicker speeds. So that's how we deduce that there was dark matter in the first place, is that galaxies were rotating at faster speeds than our theories predicted previously. Okay, so and then getting to the ultimate question is, okay, where are we going from all this? Okay, we're expanding, we're accelerating, we're cooling. What's going to happen? What's the shape of our universe? Well, this is really hard to picture. This is where it takes a lot of intense mathematical thought, and then, you know, just some different sorts of ways of doing visualizations. We have something called the cosmic critical density, the omega value. It's the average density of matter. And that's how many kilograms per meters cubed per volume of space you could pack in. Okay, so we're talking about the density of matter and the energy required to halt the expansion after an infinite amount of time. That's what the critical density is how do we actually slow or halt this expansion over an infinite period of time. So this is sort of mind-boggling to think about, but the geometry of space-time and its fate are affected by the density of the universe. You know, how much mass we pack in per volume of space will really dictate what's going to happen to our universe and what the shape is. So the critical density value, depending on the Hubble constant, is this. This is what we have so far. And, you know, what's our expansion? What kind of expansion are we looking at in the end? And what is our shape? Going on to the next slide, we have 3 scenarios. Okay, if your critical density is greater than 1, meaning if it's high, everything, there's so much gravity that it folds in on itself, right? You have a lot of mass packed in the volume of space, so you have enough gravity that it rounds the curvature of space and time around it. So it's spherical. It's a spherical geometry. And on the sphere, if you take the interior angles of a triangle, they'll add up to more than 180 degrees. So if you try to make a triangle on the surface of the Earth and measured the 3 angles, it'll be greater than 180 degrees. So spherical geometry is a discipline itself, but that's what we'd have. We'd have this closed universe is another term for it, and the shape will be spherical, and the universe collapses in on itself due to the gravity. Okay, if omega is less than 1, if our critical density is found to be if our density is found to be less than the critical density, we'll have an open universe. Okay, so we have the opposite of the sphere. It's an open saddle. We have a hyperbolic geometry here. And a hyperbolic geometry, if you add all the angles of the triangle, all the interior angles of a triangle, they'll add up to be less than 180 degrees. And we would have an infinite universe. And Olber's paradox talks about an infinite universe, if you read that, but it says the universe can't be infinite, otherwise we would see the entire sky lit up because the stars have been burning for an infinite amount of time. That's a very interesting idea proposed by Olber a long time ago. But here we are in what we currently know about our universe. Interestingly, we are at a density. We're finding the density of our universe to be equal to that critical density, option number 3. So if the density is equal to the critical density, we have this flat universe, and it's going to halt expansion over an infinite amount of time. Now, this is the worst possible type of mathematics to deal with. So the universe gave us like the most mind-boggling scenario. So this is all a 2D representation. So the math behind it gets a little more challenging. But we have this density equal to 1, and we have this flat geometry. That's what we're seeing. Okay, and to go on about this flatness problem, we found that we're so close to this critical density that it's almost exactly 1. And then so what's going to happen is this is just going to be a scenario where the universe is predicted to just flatten, cool, protons will eventually decay, and things will just basically fizzle out. That's really what the flat scenario tells us, the flat geometry based on our mass density of the universe currently. So we'll get to the end game here. What's the unknown fate of the universe? Well, it's still unknown. There's still a lot of numbers to be grappled. There's been times where we thought, well, it'll be the big crunch. There's so much gravity, the whole universe will collapse on itself. That's when you have a lot of mass. The big freeze, it's a long, slow decline. We're thinking more along that line. The big rip is when it's just torn apart by this rapid acceleration expansion. It's expanding, accelerating so greatly that everything is just shredded apart. So our likely scenario: slow decline in star formation, proton decay, universe cools, dims, and fizzles. The end. So that's still unknown, uncharted territory.